Okay, here is 6.3 logarithms and logarithmic functions. All right, so I've got this equation here in what I call exponential form. 2 raised to the third equals 8. We can rewrite this same equation. This is going to be equivalent to this equation over here. This is log form. So now I've rewritten this as a logarithm. Okay, so in exponential form, the base is the 2. That's the thing that has the exponent on its shoulder, right? And then 3 would be my exponent. And let's just look where the 2 and the 3 end up in logarithmic form. So logarithmic form, you write the word log. That's short for logarithm. And then the base is going to be a little footnote of the word log, or a subtext, if you want to think about it like that. Okay, and the exponent gets isolated, and that's really the whole point of logarithms. It allows you to isolate exponents. And so, if I had a variable there, that might be very useful. Okay, and this last part is called the argument. It's the part inside the log. I often just call it the contents of the log, but there it is. Okay. All right. So let's say it's very important that you can switch back and forth between exponential form and log form. You'll find that almost every problem in the second half of this chapter, you'll have to convert an equation from exponential to log form or the other direction. Okay, so here I've got log, and the way we would say this one, log 2 of 8 equals 3. So this is log b of a equals c. Okay, so b is going to be the base, so, and it's just so this is log form, obviously, right? We're going to convert this to exponential form, so we're going to go the other direction here. Okay, so exponential form, b is my base, okay? And then the c, that's the exponent is isolated in log form, so that's going to be my exponent, and then the a is going to go in that position, okay? All right, so there's also something called the change of base formula, and that's going to be really important because some of the calculators, a lot of them, can only work with logs with certain bases. But if you have something like this, you can rewrite this as a fraction. And it's going to be equivalent to log of a over log of b, okay? So when you don't have a base in your log, it really means you're using base 10, okay? So looking over here, there's no footnote, there's no base, but that really means this, okay? Because that's called our common log with a base of 10. That's the one that is going to be programmed into any calculator that can do logarithms. And if you think about this, 10 raised to some power is going to equal 10. It should be 1 if you think about exponential form. But just to start off with, just find the log button on your calculator, and if you hit that and put in a 10, there's not even a space for me to put in my base here, right? But I don't need a base here. This is log of 10, and this equals 1. Okay? It really means 10 raised to some power is going to equal 10. Okay? When I've got a problem like this, once you get used to logs, this is meaning 3 raised to some power equals 10. Well, 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. So it should be something in between 2 and 3, a little more than 2, so 2 point something, okay? But the thing with this is I can't put this into my calculator because I don't have a place to put the base. Some of the fancier, newer calculators, it actually will allow you it'll put a little cursor down there and you can put in whatever base you want. But if you don't have a calculator like that, then you're going to have to use the change of base formula to put it in base 10. So I'm going to write this as log of 10 over log of 3. The most common mistake I see is people get this flipped upside down. Here's how I remember which one goes on top, which one goes on bottom. If you look in log form, the 10 is higher up than the 3. So that means that log 10 is going to be higher up than log of 3, okay? And the way I'm going to put that into my calculator, log of 10. I want to close the parentheses there. That's important. And then I'm going to divide by log of 3. And remember, we thought it was going to be 2 point something. And then, hey, about 2.1, right? 2.0959. I'll call that about 2.1. Okay, because 3 raised to that decimal is going to equal 10. That would be pretty hard to figure out with guess and check. It would take you a while to get to that to a decimal like that. But let's just try it out. 3 raised to the 2.0959. I won't put in the rest of it. And, you know, I didn't put in the whole decimal, but it got me really close to 10, right? 3 raised to that power is going to equal 10 roughly. Okay. All right, so on this one, this is going to be log of 10 over log of 7. So, in other words, 7 raised to some power is going to equal 10. That's going to be 1 point something. Let's see. Log of 10, close my parentheses, divided by log of 7. And I got 1.18. It doesn't really matter if you close the parentheses on the end, but this one does matter because otherwise you'll be taking the log of 10 over another log, and we don't want to do that. We want to take the log of 10 over the log of 7. Okay, so this is about 1.18. Okay, all right. So once you get used to these, they're pretty quick. You just have to know, okay, this is going to be log of 496 over log of 5. This one is going to be log of 6789 over log of 8. By the way, I'm changing these into base 10, but if you wanted to, just to zoom out, you could use any base you want. So this would also be log base 7 of A over log base 7 of B. It's just that wouldn't be very useful because I can't put log base 7 in my calculator. I can only really put log base B. So these are going to be the common logs. I maybe should have put that in the notes somewhere. Common logs, that means base 10. Okay. All right, so I didn't finish these two down here. Got to plug those in my calculator. Let's see. Log of 496 divided by log of 5 gives me about 3.86 if I'm going to the nearest hundredth. And then move this off to the side here. Okay, and then I've got log of 6789 over log of 8. That's about 4.254. Wow. Okay. All right. There we go. Okay. Okay. On the next page, we're going to look at some inverses to start with. Okay, so I've got this exponential function here. Let's find the inverse. So remember f to the negative 1 of x, that means the inverse of x. Okay, we're not, sorry, of f of x. It's the inverse of f of x. So we're not really raising anything to the negative first power here. What we want to do to find the inverse, first step is going to be to switch the x and the y. I don't really have a y here, but let's just pretend that, let's just think of the f of x as y for now, okay? So I'm going to switch the x and the y. That's step 1. And this actually is going to be the inverse, but I want to put it in y equals form. So now I want to isolate the y, okay? So do as much as you can with our old algebra techniques. So I could subtract 1 from both sides first. So let's go ahead and do that. So now I've got x minus 1 equals 3 to the y. Okay. Now to get the y by itself, oh boy, it's in an exponent here. So some people might try to take the square root of both sides, but that's not really going to help me because then I just have the square root of 3 to the y. That's not going to isolate the y. Okay. The only thing I can do here is convert this to log form. Okay. So let's think about this in log form. So I'm going to write the word log first. Okay. My base is going to be 3. All right. The exponent is going to get isolated. So the y is going to go over there. That's going to be isolated. That's what I wanted to happen. And then everything else is going to be the contents of the log. So you could write it like this, but then it's not really clear if the -1 is supposed to be inside the log or not. So I like to write it like that so that it's really clear, okay? Because it's different if the -1 is inside the log or not, okay? And now I'm pretty much done. The only thing I would do from here is put it in function notation, since the original function's in function notation. So this is what f to the -1st of x, the inverse of x, equals. Okay, so I'm just going to put that back in place of the y. And you could flip the whole equation around too if you wanted to. You could write f to the -1 of x equals blah blah blah, right? You could do it that way. But there's my inverse. Okay, so hey, we started out with an exponential function. Its inverse is a log. All right, okay, interesting. All right, let's look at this next one. Okay, we've got e in here, which is just a number, right? It's 2.718 roughly. Okay, let's see what happens here. I'm going to switch the x and the y. So if this was my y, I'd switch that into the x, and then I switch the x into a y. And now my next goal is to isolate the y. So I'm going to start by subtracting 1 from both sides. And so I've got x minus 1 equals 2e to the y. Okay? Now, if you try to put this in log form right now, there won't be a good place to put the 2, because the 2 isn't raised to the y. This is really 2 to the first times e to the y, right? It's if 2e was in parentheses and that quantity was raised to the y, that would be different. But it's 2 to the first times e to the y. So we can get rid of the 2 like this, right? We can divide the whole equation by 2. So now I've got x minus 1 over 2 equals e to the y. So get y as isolated as you can just by adding, subtracting, multiplying, and dividing. Okay? And that's as far as I can go in terms of isolating y with those tools. But I've got another trick up my sleeve, and that's converting this to log form. Okay? By the way, you could split this into 2 fractions if you wanted to. It doesn't matter. Okay? But let's see. If I write the word log, hey, my base is e. All right? And then I've got the y is going to get isolated. All right, and the fraction is going to be the argument. That's going to be the contents of the log, like so, okay? And then looking at this log base e, well, that's my natural log. So I could write that like so, and I'd want to do that because that's simpler, okay? And then I also want to put this in function notation, so I'm going to put, that's what my inverse function is, like so. Okay? All right, so when we had an exponential function that features e, then the inverse is going to be a natural log equation, okay? So I'm guessing when I find the inverse of this, it's going to involve e, right? Because that's what happened on this in reverse, all right? So let's try this out. Switching x and y. So if this is my y, I'll switch that to x. Y is going to be the argument there. Okay, and now I want to subtract 3 from both sides. I can do that because that 3 is not part of the log. It's not inside the log. It's just a free agent out there. Okay, so I've got x minus 3 equals the natural log of y. Okay, and then you have to really understand what natural log means. That means a log with a base of e. So you could write this as log base of e to the y. Okay, you don't necessarily need to write it like that, but you need to know that's what it means, because next thing we're going to do is convert this, right? I'm trying to get the y isolated. I can't really get any farther without converting this. So this is in log form. I'm going to convert it to exponential form. So my base is e, okay? The part that's isolated is the exponent. So that's going to be x minus 3, the quantity x minus 3. That's my exponent. And then, hey, my y is isolated. Okay? And then I'll just put it back in function notation. And there we go. Okay. All right. let's graph some exponential functions. I'm going to do these pretty quickly because this is really a lead into something else. We've already graphed some exponential functions like this. So this one, I can see that it's going to be exponential growth because the base is more than 1. This one should be exponential decay because the base is less than 1. Okay, so both of these are going to have an asymptote, a horizontal asymptote, right on the x-axis. Okay, and then let's find the x and y intercepts. Well, let's start with the y-intercept. Okay, so I'm going to plug in 0 for x to find my y-intercept because I know any point on the y-axis has an x-coordinate of 0. Hey, 2 to the first equals 1. So, hey, there is my y-intercept. Now, the x-intercept, there actually isn't going to be an x-intercept because I've got an asymptote. And an asymptote, that's going to be a guide for the curve. So my curve's going to approach that line but never touch it and never cross it. So that means that I'm not going to have an x-intercept. Okay? If you tried to do it algebraically, then I'd have, I'd plug in 0 for y. 2 to the sum power equals 0. Well, 2 to the 0th equals 1, right? 2 to the first equals 2, and so forth. Well, what if I try a negative number? 2 to the negative first would be 1 over 2 to the first, would be 1/2. So no matter what, you can't take 2 and raise it to a power and get 0. It's not happening because there's no x-intercept, okay? So you could plug in other points if you wanted. You could see what happens when you plug in -1 and +1 and so forth. But what we're going to get is an exponential growth curve that goes through that point like so, okay? This one, we're going to get exponential decay. Let's find the y-intercept. 1/2 raised to the 0th equals 1, right? Anything raised to the 0th equals 1. So it's going to be decay going through that point. Okay, and again, you could plug in other x values to get more info, but that's basically what those parent graphs are going to look like. Okay. Okay, on the next page, we're going to graph this function actually. So it says, okay, f of x equals 2 to the x. That's what we just graphed here. We're going to find the inverse of that. It's going to ask us to graph this function and its inverse on the same graph. Well, hey, let's just copy our work there for f of x. So here, I'll use a red pen here. So I've got an asymptote there, a y-intercept at 1, and its exponential growth. Okay. So I'll label, there's f of x, and I'll label that because we're going to put another graph on that same axis. Okay. But before we graph the second function, let's find it. So the second function is going to be the inverse of f of x. Okay, so I'm taking this and switching the x and y. Okay, I want to isolate y. Well, nothing I can do with adding, subtracting, multiplying, dividing. So I want to put this in log form. So my base is 2. The y is going to get isolated, and there's only one slot left for the x. Okay, so there we go. Here's my inverse function. Like that, okay? All right, so let's graph this. Well, we've never graphed a log function before, but if you know something about graphing inverses, it's going to be reflected over the line y equals x. So this is something that maybe you did in geometry, reflecting over a line like that. So y equals x goes through 0, 0, has a slope of 1. Okay, and so another nice trick for these, if you look at this point, this y-intercept that I have on the original function, that's the point 0, 1. And if you just switch that x-y pair, then it's going to be reflected over the line y equals x. So 1, 0 is going to be on the inverse function. Okay? And you could get other x, y pairs and do that as well. So this would be 1, 0. Okay? But if you kind of think about the mirror image of this, if we folded this paper in half over that line, what's going to happen is it's going to curve kind of like this, okay? Let's get this is also going to have an asymptote, but it's not going to be this axis, okay? Because if we took any point on this axis and reflected over the line y equals x, then we're going to get this, okay? It's going to be on the y-intercept instead. So my logarithmic function is going to have a vertical asymptote, okay? And then I'm kind of just doing a mirror image thing here. It's going to look something like that. This is going to be my inverse function, okay? So just to give you an idea, logarithmic functions are going to have vertical asymptotes, and they're going to be curving, either that way or that way, depending on the base. All right. So that's what they look like. Okay. So let's graph a couple more of these. All right. So these particular ones are going to have the same vertical asymptote as the previous log function. Actually, hey, wait a second. This is what we just graphed there. So let's just this is the same from the last problem. So, okay, that's going to have that point on there. Okay. And then this one is still going to have the same vertical asymptote. So it's important that you include that in the graphs. Okay. And then we need to figure out which way the curve's going to go. But I'll get to that in a second. First, let's find, it's not going to have a y-intercept, right? Because these points are off limits, but it is going to have an x-intercept. So let's find our x-intercept, and we can find that by plugging in 0 for y. Okay? All right. So, hey, let's put this, I can't really put this side into a calculator, but I can convert this into exponential form. 0.5 raised to the 0th is going to equal x. Well, anything raised to the 0th equals 1. So that means, hey, I got the same x-intercept again, okay? But the difference with this one, as opposed to the last equation, when the base is more than 1, when the base is greater than 1, I still think of this as growth. Okay, it's not exactly exponential growth, but it's still, this curve is going uphill if you read it from left to right. It's going uphill, right? This curve, since my base is less than 1, then it's going to, I think of it as decay, which means it's going to go downhill from left to right. So it's going to look more like this. Okay, so it's still going to use that asymptote, but it's going to approach it in that direction. Okay, and you could find other xy pairs to get more information about the graph, but in general, that's what you're going to get. Okay, and your asymptote is going to stay on the y-axis as long as there's nothing added or subtracted to the x. Okay, on the next page, we are going to add or subtract something from the x, but I'll show you how to do that in a second. But if there's nothing added and subtracted inside the log to the x, then you got the y-intercept, okay? All right, on the next page, we do have something added or subtracted to the x. We got that 1, okay? So to find the vertical asymptote, so it's important you just remember that it's going to have a vertical asymptote. If it were an exponential function, it would have a horizontal asymptote, so you really need to memorize that, okay? But this log function has a vertical asymptote, and the way I'm going to find that is by taking the argument, the contents of the log, and setting it equal to 0. Okay, it works kind of like finding the x-coordinate of a vertex of a parabola or something, okay? So then the line x equals -1 is going to be my vertical asymptote. Okay, and then I'm thinking, is this growth or decay? Well, this one's going to be growth, so then I know it's going to go uphill from left to right, so it should look something like that, right? So I got a general sense of what it's going to look like. I still want to find some points. I want to find my intercepts, okay? This one is going to have an x-intercept, just like the other log functions we've done. So let's plug in 0 for y into the function. Okay, and my goal here is to solve for x. So some people try to put this in to convert this to exponential form right now, but I don't want to do that yet. I want to take care of the 3. I want to add 3 to both sides because you do everything you can with addition, subtraction, and multiplication and division to begin with. But using those 4 techniques, then we're at a dead end here, right? And now's when I'd want to convert this. So 2 is my base, 3 is my exponent, and the contents of the log are going to get isolated over here. Okay? So, okay, 2 to the third equals 8. And now I can subtract 1 from both sides. Whoops. Subtract 1. I was thinking I'm already doing the subtraction in my head. So that's 7. Okay, so my x-intercept is 7. All right, hey, that just fits on this graph. What do you know? There's my x-intercept, okay? I didn't find the y-intercept on the last 2 problems because there wasn't one, because the asymptote was right there. But this is going to have a y-intercept. There's nothing wrong with having points here. They're not on the asymptote. So let's find the y-intercept. And to find a y-intercept, you're going to plug in 0 for x into the original equation. Okay? So, okay, 0 plus 1 is just 1, so let's simplify here a little. Okay, what I see often is that people will take this and they'll say, oh, that equals, that's equivalent to y equals log of, log base 2 of negative 2. But that's incorrect. You can't combine these because the 1 is inside the log and the negative 3 is not. Okay? So what I want to do instead is find the value of this log first, then subtract 3 from it. Okay? So I could put that into my calculator by changing the base. I'm going to do log of 1 over log of 2. And once you get used to this, you can actually do that without a calculator. 2 raised to some power equals 1. Well, it's going to be 0 actually, right? 2 raised to the 0th equals 1. So let's see if that works out here. Okay. Okay, so I've got log of 1, close my parentheses, divide by log of 2, and I got 0. So y equals 0 minus 3. So y equals negative 3. So that means my y-intercept is negative 3. Okay, and if you remember when we're thinking about growth or decay, I kind of thought it would be an uphill curve like that from left to right. And that works out with the information we have, right? So now we can draw a pretty nice curve that goes through those points and also follows the asymptote. Okay, and that's the end of the section, and I will see you next time.